Alrighty, folks. Today we are going to be talking about magnetic domains. And effectively, what that means is we are talking about how magnets become magnets. And what you kind of see here is someone trying to herd kittens. And what I want you to ultimately see today is that getting a material to be magnetic, it's actually a little bit like trying to herd kittens. You have to have a lot of things go exactly right. And then even once you have it all set up, it may not stay magnetic for very long, just like these kittens won't stay lined up. So let's go ahead and jump into it. All right, setting up your notes today. Your essential question is what makes a material magnetic? And your guiding questions are how do electrons relate to magnetism? What needs to happen on an atomic level for a material to be magnetic? What materials can be magnetized? And how do you magnetize a ferromagnetic material? In addition, in your packet, you will see a magnetization flowchart. So I'd like you to have that accessible as well. So what we're going to do is you're going to take your standard notes, and then after each note slide, we're going to jump over to the magnetization flowchart and put some information there so that we can kind of come to understand how are magnets made. All right, our learning target for today is I can explain why some materials are magnetic and others are not. So let's start off with this. We're going down to the very basic level, the most base unit of matter, and that is the atom and its subatomic particle, the electron. So hopefully you remember, electrons orbit the nucleus of an atom, and that means that they are also, or they are in motion, and also they are rotating or spinning. So when you combine the fact that electrons have a charge, they have a single negative charge, they are in orbit and they are spinning, this actually makes an electron a tiny little magnet. Now, electrons mostly occur in pairs, and these pairs have opposite spins. And when you have opposite spin electrons, they are going to cancel out each other's magnetic effects. So most materials in the world have most of the electrons paired up, and therefore most materials are not magnetic because those electrons, just we get down to the most basic level of atoms, and the electrons are paired up and their magnetic fields cancel out. But what happens when you have unpaired electrons? So on your chart, we're going to start here at the very top center, and you're going to write electrons. And then over the arrow here, we're going to say what happens when the are paired, meaning that the electrons are paired and they cancel out each other's magnetic field, resulting in non-magnetic material. However, when electrons are unpaired, that means that they have magnetic fields, because if they are unpaired and they don't cancel out, then they are tiny magnets, and we know that all magnets have magnetic fields. So what this then leads to, okay, so as we said, unpaired electrons produce magnetic fields. Now, usually when materials have one or more unpaired electrons, their atoms field don't line up, and this makes an overall weak magnetic field. So think back to when we were talking about magnetic fields, and we have those arrows. So you'll remember that when you have because electrons are tiny little magnets, that means they have poles, north and south poles. And if you have two north poles facing each other, their fields don't line up, and in fact, they repel each other, so the field is weaker. Or maybe they're just kind of slightly askew, and their fields just aren't very strong. So usually that's going to be the case, and just the result is a weak magnetic field, and you don't have much magnetism. However, if you have a bunch of atoms' magnetic fields align, that is going to create a magnetic domain, because all of these magnetic fields are pointing in the same direction, and that makes them get stronger and stronger. The more tiny magnets you add to that, the stronger your magnetic field becomes. And this becomes a magnetic domain, which is a region that has a large number of atoms with aligned magnetic fields. And magnetic domains have strong magnetic fields. So let's think about it in terms of ants. I'm giving you a metaphor here. So each ant on its own is not particularly strong, okay? But let's say that there was just a grape sitting on the ground, okay? One ant probably couldn't move that grape. However, if you get a bunch of ants working together, all of a sudden, these ants, their strength is amplified and they are able to move this object that's so much bigger than them because they're working together and they're much stronger. I'm sure you've seen this before, a group of ants carrying some big piece of food that's so much larger than them. This is similar to magnetic fields, or electrons and their magnetic fields. Each individual electron, its magnetic field isn't that strong. And if you have all these electrons pointing in the same direction, they're not really going to do much. However, when all of the electrons align and are working together in the same direction, just like the ants all aligning and working together in the same direction, they become much stronger and they make a stronger magnetic field or a magnetic domain. So we have our magnetic fields. If they are not aligned, meaning they face random directions, you're going to have weak magnetic fields and the material is going to be non-magnetic. However, if you have magnetic fields of electrons from the atoms and they are aligned facing the same direction, you're going to have strong magnetic fields. Those are going to cause magnetic domains. And now we're going to talk about ferromagnetic materials. So if you zoom in with really strong microscopes on a magnetic material, you can actually see the magnetic domains. This is zoomed in really, really closely. And you can actually see the magnetic domains and their alignment here in these little groups. So these are actually like groups of atoms, giant, large groups of atoms with all of their magnetic fields aligned. So you can actually zoom in and see these magnetic domains, which is pretty cool. So, ferromagnetic materials. Metals like iron, nickel, and cobalt, they have enough unpaired electrons and the atoms align and make magnetic domains. So, this is when we're defining a ferromagnetic material, it is a material such as iron that can be magnetized because it contains magnetic domains. So, when we are looking at a material like iron, normally its magnetic domains are not aligned. So if you just have like an iron nail, it's not going to be automatically magnetic, okay? And that's because its magnetic domains are all pointing in different directions. And as we said with the electrons, the magnetic fields, if they're not aligned, they aren't going to be very strong. And so they don't produce a magnetic or a strong magnetic field. However, if you get all of the magnetic domains, or most of them, pointing in the same direction, now all of these magnetic fields are aligned in the same direction and they are stronger and they're amplifying each other. And this means that the material is magnetized and now you have a magnet. So what we need to look at here is if your magnetic domains are not aligned, they're all facing different directions, the magnetic domains cancel each other out and the material is non-magnetic. But what if that's not the case? We now enter the world of magnetization. So if a non-magnetized ferromagnetic material is placed in a magnetic field, it will cause the domains to align that is because when the magnetic field is stronger than the magnetic field that's being placed in is stronger than all of the individual fields of the ferromagnetic material in the magnetic domains. And so that magnetic field they are all going to then rotate and align so that they align with that external magnet. And now all of a sudden, all of your magnetic domains are in the same direction. So that is how you go from this like non-magnetic material with no external magnetic field, and then you line up or you place it next to a strong external magnetic field and the magnetic domains become ordered. And now, because all your fields are facing in the same direction, now you have a strong magnet and this material is magnetic. So here's the thing. Atoms are in constant motion and domains become disorganized after time. This is just a law of nature, and magnetization is lost. And so once you remove that strong external magnetic field, no matter how strong it was, immediately after moving it, the magnetic domains begin to revert. So it's a question of what kind of magnetic field did you apply? Is it a weak magnetic field? If so, your magnet only is going to be temporarily magnetized. So think back again to that nail, an iron nail. If you just take a little like refrigerator magnet and you attach it to a nail, the nail will actually become a magnet as long as that refrigerator magnet is attached. But as soon as you remove it, that magnetism is going to be lost. However, if you took that nail and you exposed it to a strong magnetic field. So this could be done in a number of ways. You could expose it to a big, strong magnet, an electromagnet, or you could take a weaker magnetic field and you could do repeated exposure. And we'll actually do this in class when we make a compass ourselves. But you can do repeated exposure and turn that and simulate a strong magnetic field. And then it'll become, quote unquote, a permanent magnet. Now, a permanent magnet is not actually permanent because given enough time, even the strongest magnet will ultimately become non-magnetic because of the motion of atoms. So one thing you can also see here is how all of these are aligned, or how the magnetic fields align. And we know that those arrows, we've seen them on magnetic fields, means that there are poles. There's a south pole and a north pole. So if you were to break this magnet in half right here, you would actually end up with two smaller magnets, because if you break it in half right here, the top half of this bottom magnet is going to become the new north pole, while the south pole stays the same. And on this top magnet here, the bottom part of this magnet is going to become the south pole, because that's the bottom of the south pole of all of the magnetic domains. And this top part is going to become the north pole, because it's the north pole of all the magnetic domains. So very important to know, when you break a magnet in half, it's going to create two new magnets that both have north and south poles. You cannot have a magnet with just one pole. All right, so if we have magnetic domains and ferromagnetic materials, and all those magnetic domains are aligned, if you're using an external weak magnetic field, you'll have a temporary magnet, and using a strong or external strong magnetic field, you'll have a quote unquote permanent magnet. All right, folks, so what I want you to do now is turn to your bar magnet diagram in your packet, and you should have a magnetic field drawn onto your diagram. What I want you to do now is go ahead and draw your magnetic domains into this magnet. And remember, the magnetic fields of your domains should line up with your poles. And so make sure that whatever you have happening in here is going and continuing with the lines that you have established for your magnetic fields. So right here also, you can kind of see I have this little tutorial that you can find. You can read through here, and it does a really good job of explaining ferromagnetic materials and magnetic domains. But I just want to show you this real quick. As I bring the magnet closer to this, you can start to see with a weak ferromagnetic material, or with a weak magnetic field, you have some of the magnetic domains align, but as we get closer, more and more of the magnetic domains begin to align with the magnet, and this ferromagnetic material becomes more and more magnetized. So, as we said before, making a magnet's a little bit like kittens, herding kittens like this. You know, you have to get your electrons to be unpaired, and then you have to line up your atoms with your unpaired electrons so that their magnetic fields align, and that'll create a magnetic domain. And once your magnetic domains are aligned, then you have to align all of your magnetic domains in the ferromagnetic material in order for that material to become magnetized. And so you can see with these kittens, you can kind of move them all around, and you can get them kind of like they're in order, kind of, but then just like any magnet, at a certain point, they're going to be, just like because the atoms are in motion, they're going to become disorganized. The material is going to become non-magnetic. Just like these kittens, they're not going to stay in line, and they're going to, once again, move into random directions. All right, folks, got a 4-question quiz. Go ahead and pause this video, take the quiz, and then come back. Which of the following are properties that cause electrons to be tiny magnets? Well, you're going to need them to be orbiting the nucleus, spin, and charge. Remember that equal number of protons have nothing to do with magnetism. In order to form a magnetic domain, atoms need to have what? Well, they need to have unpaired electrons, and that can't be the case if they have even number of electrons. and they also need to have aligned magnetic fields. A material such as iron that can be magnetized because it contains magnetic domains is a ferromagnetic material. Fun fact, ferro is, I believe, the Greek word for iron, so it's right there in the name. If you break a magnet in half, then remember we said each piece is now a magnet with a north and south pole. All right, so if you did that, you should have gotten 4 out of 4. Alrighty, folks, so that's it for magnetic domains. Make sure that you have your chart complete. And now that we understand magnetic domains, going forward, we're actually going to use that information to make our own magnets. All right, have a great day.